A finite matrix's eigenvalues appear as discrete, isolated points. But in infinite dimensions, operators on continuous function spaces generate a spectrum that expands into a continuous region in the complex plane. This region provides a signature of the operator's behavior, defining its limits. For bounded linear operators on complex Banach spaces, the spectrum occupies a region that is strictly compact and bounded, following a specific algebraic structure. Locating this region requires us to look past the determinate formulas of linear algebra and move toward the tools of operator theory. Understanding the topology of the spectrum, how it is bounded and where it breaks down, reveals the logical constraints governing infinite dimensional systems. This analysis takes place within complex Banach spaces, vector spaces that are complete and equipped with a norm, using a bounded linear operator denoted as T. To identify the boundaries of the spectrum, we use the resolvent operator, defined as T minus lambda times the identity, inverted. We also track the operator norm, which defines the maximum stretch of the operator T. The resolvent set requires lambda where the inverse operator exists, is strictly bounded, and defined on a dense domain. The spectrum is the set of all remaining points, the locations where the inverse operation fails to meet these criteria. Mapping the spectrum is the process of determining exactly where in the complex plane the resolvent operator ceases to function. Theorem 7.3-1 establishes the mechanism for operator invertibility, beginning with a specific constraint. The operator norm must be strictly less than 1. When this condition is met, we can construct a finite partial sum, adding the identity operator to successive powers of t. If we multiply this sum by the quantity I minus t, the middle terms cancel out, leaving a simplified expression, the identity minus t to the power of n plus 1. Since the norm is less than 1, as n approaches infinity, the term t to the n plus 1 diminishes until it disappears. In a complete Banach space, this absolute convergence confirms that the infinite series, the Neumann series, defines the inverse operator. This convergence provides the analytical basis needed to determine invertibility across the complex plane. Using the Neumann series, we can prove the resolvent set is topologically open, which inherently forces the spectrum to be a closed set. We start at a known regular value, lambda sub 0. Around this point, we can define a disk with a radius equal to the inverse of the resolvent's norm at that specific location. To evaluate any point lambda within this disk, we factor t minus lambda sub 0I out of the general expression. This factorization reveals a term that follows the same structure as our geometric series. As long as lambda remains inside this radius, the bracketed term satisfies the Neumann series convergence criteria, confirming the inverse exists. Because every regular point is surrounded by a neighborhood of guaranteed invertibility, the resolvent set is an open domain. This necessitates that its complement, the spectrum, must be a closed set. The spectrum is strictly constrained by the operator's norm. It simply cannot extend infinitely across the complex plane. We define a circular boundary with a radius equal to the operator norm. By analyzing the operator for values of lambda that exceed this norm, we isolate a term in the form of I minus 1 over lambda times t. If the absolute value of lambda is greater than the operator norm, the Neumann series converges. This confirms the inverse exists for every point outside this boundary. The smallest disk that fully contains the spectrum is the spectral radius. Because the spectrum is both bounded by the norm and closed, it is a compact set, a finite region of complexity in the infinite plane. The Resolvent equation, or Hilbert relation, reveals how the resolvent operators at different points in the plane are linked through their distance from one another. Algebraic substitution shows that these operators commute, meaning their relationship is dictated by the scalars involved. This leads to a question of symmetry. If a polynomial is applied to an operator, does the spectrum undergo an identical transformation? The spectral mapping theorem shows that it does. When we factor an operator polynomial, the roots match those of a standard scalar polynomial. If the overall operator polynomial cannot be inverted, at least one of these root factors must also lack an inverse. That failure identifies a scalar value that belongs to the spectrum of the original operator. This demonstrates that the spectrum reflects the operator's algebraic structure, allowing operations to be mapped directly onto the spectrum. The architecture of the complex plane shows the spectrum as a compact shape contained within a disk defined by the operator norm and surrounded by the open Resolvent set. The Neumann series defines these boundaries, establishing exactly where the inverse operator ceases to exist. Through this analysis, we have derived three laws. The Resolvent set is open, the spectrum is compact, and the relationship between the operator and its spectrum is algebraically symmetric. These topological rules apply not just to general spectral values, but to point spectrums and eigenvalues as well. In functional analysis, an infinite-dimensional operator spectrum forms a closed and compact set, strictly governed by the constraints of the operator's own norm.